right, so we previously talked about finding the area under a curve by approximating using rectangles or trapezoids, but now we're actually going to talk about a method of approximating this area called integration. And integration looks like this. So we're going to talk about the properties of definite integrals. Integration looks like this, where a definite integral is this whole like swoopy line here from a to b of f of x dx. So what does that mean? Well, b, this is called the upper limit. A is the lower limit. So that's easy enough to figure out. This swirl thing here, swirl? I don't know what to call it, but that's actually the integral itself. That's the integral. And f of x is our function, okay? But you can actually just call that the integrand. Ooh, so fancy. And this is the variable of integration. This dx is the variable of integration. What we're integrating with respect to. And this whole entire thing here is called a definite integral, all right? So this entire thing here, that's a definite integral. Now, what's an indefinite integral? An indefinite integral does not have these limits here. It doesn't have the upper and lower limits. But the definite integral does. So the integral, if we wanted to read this, we would say this is the integral from a to b, a definite integral from a to b of f of x with respect to x, right? So the definite integral from a to b of f of x with respect to x. This dx means with respect to x, right? Okay, so what is the integral? It's finding the area under a curve. And here we're given the function y is equal to f of x, and we want to find the area under this curve. So to do that, you basically just start calculating here, okay? So here, these are going, looks like we're going by ones here. So this little triangle here, and as you know, I never draw these real accurately, okay? But it looks like we're going up 4 and over 2, so this is going to be an area of 4. Here we're going to have an area of probably, well, I've actually already calculated these, so hopefully you can just trust me. But the area here is going to be 20 underneath this, right? And you could do that by finding this. So you've got 1, 2, 3 times, what is that? Well, anyway, this whole thing, I wanted to say that this whole thing, not just this rectangle, is 20, but 3 times 4, so this is going to be 12, okay? And this is going to be 2 times 4, which is 8 divided by 2 is 4. And again here, 2, 4, so 12 plus 4 is 16 plus 4 is 20, is that whole thing there. Here, we're going to have, this is over by 3, I believe, yep. So 3 times 1, this is 3 halves. This is going to be 2 times 3 is 6 divided by 2 is 3. This is 1, 2, 3 times 3 is 9, okay? And then this here, we have a circle with a radius of 1, 2, 3. So the area of a circle, you might remember, is pi r squared. So our area is going to be equal to 9 pi, but because that's just half of a circle, our area of the semicircle is equal to 9 halves pi. So 9 halves pi. And actually, something I didn't tell you is that because these areas are below the x-axis, they're actually negative, all right? So these are actually thought of as negative areas. And that's going to be important when we're calculating this. So here, we're asked to find the integral from 0 to 7 of f of x dx. Well, from 0 to 7, we're going to go to here. We take 4 plus 12 plus 4. 4 plus 12 plus 4, that's just equal to 20. Boom, we did it. What about from 0 to 13? Well, from 0 to 13, we're going to have, I already calculated up to 7, which is 20, plus we've got a negative 3 halves plus a negative 9 plus a negative 3. If we add that up, I think we're going to have 6.5, right? Because you're going to have to add these and then subtract them from 20. Okay, what about from 0 to negative 6? Well, here we're going backwards. From 0 to negative 6. Well, from 0 to negative 6, we've got negative 9 halves pi. Okay? What about from 3 to 3? 3 to 3? Well, if I start at 3 and I go to 3, I haven't gone anywhere. I haven't found any area at all. So that's just going to be equal to 0. What about from 7 to 0? Well, I already found from 0 to 7, right? I found from 0 to 7. If I go from 7 to 0, I'm going backwards. So I'm actually going to have a negative 20. If I go from 10 to 4, I have from here back to here, right? So, that's kind of complicated, but it looks like I can rewrite this as a negative 4 to 10 of f of x dx, and that's actually the exact same information. So this is going to be equal to, so this is 4, what do I have here? 2 times 3 is 6, right? So that's 6 there, negative 6. So I have negative 4 minus 4 plus negative 3 halves plus a negative 9. So messy to write, but anyway, I think the answer we're going to get is a negative 1/2, hopefully. You can check my math on that. And I think that you're kind of getting the idea here, all right? So from negative 8 to 13, from negative 8 to 13, that's our entire graph here. So I'm going to have, look at this, 4 minus 9 halves pi plus 20 minus, this is all 27 halves. So that's all going to be equal to 10.5 minus 9 pi over 2. Okay? Well, now we're asked to kind of go back to some things we already knew. What's our derivative at f prime of negative 6? This is f of x. So at negative 6, what do we have going on here? Well, we go from a straight line to a curve. We actually have a cusp. So it's undefined, right? What about f prime at negative 6, or f double prime at 6? Well, at 6, our derivative here looks like it's 1/2, right? Or negative 1/2. But the derivative of that, the second derivative, is going to just be 0. It's constant. Okay, what about our average rate of change? Oh, I don't think you could see that. But anyway, there you go. It was constant. The average rate of change from 0 to 5. Well, that's going to be f of 5 minus f of 0 over 5 minus 0. Well, f of 5 is equal to 4, right? F of 5 is equal to 4 minus 0 is equal to 0 over 5 minus 0, which equals 4/5. Okay, a couple of more things, just a little bit before we dive into our properties here. True or false? The integral from 0 to 2 of f of x dx plus the integral from 0 to 4 of f of x dx is equal to the integral from 0 to 4 of f of x dx. Let's go for that. 0 to 2 would be 4. 2 to 4 here, it looks like it would be, what was that, 8 maybe, right? All right. And then from 0 to 4, we're just going to have, well, 4 plus 8 is 12, and it looks like 4 plus 8 is still equal to 12. So I believe that this is true. This is true information. And when, finally, is f of x not differentiable? Well, when x is equal to, let's look up here. When is it not differentiable? Well, it's not differentiable at negative 6, okay? It's not differentiable at 0. It's not differentiable at 2. It's not differentiable at 5. It's not differentiable at 7. Right? 5, yep, 7. It's not differentiable at 8. And it's not differentiable at 11. A lot of places it's not differentiable. Why? Because there's cusps there. So let's go over and just review some of the properties of integration. I've written them down here. I think that they're mostly kind of self-explanatory, but let's just look here a little bit. We've got, if f is defined at x equals a, then from a to a, f of x dx is equal to 0. You saw that earlier. If it's integrable, ugh, what a hard word to say, then a to b is equal to the negative b to a. You can flip them around. If it's integrable on the 3 closed intervals defined by a, b, and c, then a to c is equal to a to b plus b to c. We already talked about that. If f and g are integrable and k is a constant, then the integral from a to b of k f of x is equal to k times the integral. You can pull that constant out. The constant from a to b, k is just a number here, is equal to k times b minus a. And a to b of f of x plus g of x dx, that can be broken up into plus or minus. Okay, so let's just do a few examples here, and then I think, yeah, that's all we're going to do. Let me a second. Yeah, that's all we'll do. I don't think it's really too complicated. So given that a to b of f of x dx equals 8, a to b of g of x dx equals -3, and a to b of h x dx equals 5 halves, we're going to calculate all these. So b to a of g of x, well, a to b is -3, so b to a must just be a +3. A to b of 2f of x is just going to be equal to 2 times 8, which is equal to 16. All right. A to b of 5 dx, that's just going to be equal to 5 times b minus a, right? We don't know what a and b are, so we just have to use variables there. A to b of 5 plus g of x is going to be equal to 5 times b minus a, plus the integral of g of x is a -3. So I can rewrite that as 5 times b minus a minus 3. A to b of f of x minus h of x dx is going to be equal to 8 minus 5 halves, which is equal to, right? 8 minus 5 halves, which is going to be equal to 16 minus 5, which is 11 halves. Okay? And a to 4 of h of x dx plus 4 to b of h of x dx is equal to the integral from a to b of h of x dx, which is just equal to 5 halves. Okay. There is more to this, but honestly, I don't think you really need it. It involves kind of calculating integration using some awkward formulas. Let me pause for a second here. Yeah, I'm going to stop here. I think the last page of the worksheet is just honestly kind of a waste of time, so we're not going to do it. All right, if you have questions about this, leave them in the comments. Hopefully you have a pretty good understanding of how definite integrals work, and I will see you in class. Goodbye.